I'm Ioannis, and today I'm going to talk a bit about explainability and how we go from philosophy to machine learning and AI adoption. Who am I? I'm Ioannis Bakagiannis. I'm as Greek as feta cheese. I've been to McGill University to computer engineering. I did my master's there for 2 years, and it was focused on convex optimization and machine learning. I've been working at RBC since I graduated for 5 years right now. And I had roles as a data scientist, machine learning architect, even product at some point, since we were very, and we still am very independent to pursue my projects. And my interests usually revolve around natural language processing, anomaly detection, and lately ethics. I kind of like how the field is shaping. And today we're going to talk about explainability. So Lewis defines explainability or explaining. To explain an event is to provide some information about its causal history. So if I'm trying to convey my beliefs to you, this is going to take some knowledge transfer and some background on the causal history of the event. And explainability is mostly linked with causality. That is happening in the AI field too. As Joseph mentioned, an explanation is an assignment of causal responsibility. There are many theories about causality, but most of them, and the most interesting to AI, are those ones that deal with counterfactuals. The counterfactual is a hypothetical. If an event A happens, if an event happen, if an A happened, if an event B did not happen before that. So it's hypotheticals about event co-occurrence, let's say. But co-occurrence of events does not give useful causal information. Think about the events of rain and rainbow, and rain and me eating pancakes at the same time. I might be eating pancakes because it's a Sunday morning and I like pancakes on Sunday morning. But it might be after rain, but that has nothing to do with that co-occurrence. Another notion of causality is necessary and sufficient causes, and a cause should be both to be complete. And the last concept of causality that is really important is this notion of causal chains. And you can see that general explanation is a guided tour through the causal chain. And what that causal chain means is you got events and they're linked through, let's say, on a temporal basis. So if C happens before E, then the cause has to be C, right, to event E. And events that without a root cause are the events without a cause are deemed as root causes. A causality example would be in that rainbow events. Of course, they are correlated since most of the time that it rains, we have rainbow. It is a necessary but not a sufficient cause. So it needs to rain before we see a rainbow, but not all the times we see a rainbow after a rain. A causal chain that the rain must happen before the rainbow, the event of the rainbow appearing. The counterfactual that we said before, a hypothetical would be to have a rainbow without the rain. And that's how we argue that rain is a cause to the rainbow, because there is no hypothetical that there is a world that without rain we could have a rainbow. And that's why explanations usually are constructive. They're sought in response to those counterfactual cases, and that's how you build explainability. Causality in AI. Unfortunately, causality in AI it's a bit tricky. Up until now, correlation would assume causation, and lack of robustness could be viewed as causation. Right now, the most widely known interpretability algorithm out there is LIME, which interprets feature importance into somehow causality, which is not exactly the case. On the other hand, adversarial examples can be part of counterfactual reasoning. So imagine if you come up with adversarial examples and you don't see any rain over there, that it doesn't crumble your view of the world, then you can say, yes, that is a cause for that event. And lastly, which is tough for any math person, probability is used only to strengthen or weaken a cause, but it's not a standalone cause of something happening. You can assign probabilities to an event or high probabilities to some high correlation, but that doesn't really mean something without the narrative. Another concept of explainability is this explanation bias that we have as human beings. If I'm trying to, it's in every one of us, speaks a kind of different language. We have, based on our experiences, we have developed biases, and the same word does not mean the same to any of us in here. When I say responsibility or I say projections, that could mean different things in our heads. And so, since there are multiple explanations based on the granularity and the selection of the causal chain that we're looking at, people have biases on those explanations. They can accept and reject explanations based on their particular biases. And that's the abductive reasoning, not deductive, abductive or inductive. Abductive reasoning, which is inference to the best explanation. So meaning we're doing all that and we give the hypothesis that explains the event better than everything else. So what an example would be, you're a detective and you're trying to solve a murder. You have suspects, evidence, motives as the available parameters. With abductive reasoning, you're trying to find the best explanation for each suspect that best fits evidence and motives. But if you want to encounter a murder that had the same parameters, you would incline to a certain outcome more. For example, you're racist and you're saying, based on history, a certain type of people are more inclined based on your worldview. You're going to try to give an explanation like that, and that's the more convincing explanation to yourself. And at the same time, the causal chains, you could use them in as thin or thick as you like. So, for example, one can find the murderer, but the root cause of that murder is not the person. Maybe the murder was done because somebody was very poor and was trying to provide for his family, and then the actual root cause of that murder was the poverty or the social situation of the person. Explanation bias in AI, it's kind of tricky. Our models right now that we have do not have the ability to do any of that. Derive causal chains or more than one causal chains, give different hypotheses and matching them with the biases of the people. So what makes sense is to find to develop explanatory agents that they're sitting on top of the machine learning systems. And these agents would be hierarchical to resemble a causal chain. And they could have the ability to derive from a single outcome different explanations. And then actually serve the best explanation to the explaining to the person that is needed the explanation. But how you convey in everyday, how we convey our thoughts and beliefs. If I want to transfer my beliefs to you, that would be based on conversation and interaction. I would try to pick your brain and try to convey and project my thoughts and beliefs on you. And that's the thing, that's a projection. If we're not on the same page or in sync with the person that we're interacting with, we're not going to be able to relay that explanation to them. So knowledge transfer and explanation is a social thing. It's a dynamic phenomenon where the explainer tries to find the best explanation to the occasion. It does that inductive reasoning. And usual explanations are done in a natural language, but it's not limited to that interaction. So now, how social explanations fit in AI? We have to build human-machine interaction interfaces. So under the hood would be that explanatory agent, and on top of that, there's going to be an interface that the human will interact. And these agents will dynamically interact with the explainee in order to provide the best available explanation. And that's a dynamic feedback optimization every time. Also, in order to do that, we have to understand the features of the models themselves. For example, in a classifier, in an image classifier, there is at some point some feature maps that they focus on different things. For example, you could have a feature map focusing on how many legs an animal has, but we can't really name it. So we have to go in, see what the model does with the picture, and then say, the model right now is trying to predict how many legs are in the picture. For a human, it's 2. For a horse, it's 4. But then we don't have the ability to do that without a person going in and looking at it. And at the end of the day, it has to have at some point a natural language component to make it more real and more believable. What I've summarized exists in these 3 papers. You can go ahead and take a look. They have way more information that I could give in this talk. And thank you for listening. Actually, I was a bit lazy here. I put I just recently started a podcast and I did some artwork, and that's my going away slide. So I thought it was fitting to put it there. And I'm open to any questions that the audience has.
Nice one, Ioannis. Thanks so much for that. Look, really appreciate you taking the time and sharing your thoughts. Some very interesting topics there. I'm not having a technical background myself. It's always interesting to kind of get into these really nitty-gritty conversations that aren't necessarily technical. But yeah, definitely a lot to learn from my end. So, yeah, definitely. We had a question and then it disappeared on our polls section. So. The question is, if you have an explainable model that is less accurate than a deep learning model that is more accurate, which one would you choose? Assume no overfitting in deep learning. Have you encountered such a situation?
Sure. Because right now we have couple deep learning models in production, our team. And that was a frequent question. The thing is that it's on what I said on the slide, I think 5 or 6. It's based on that correlation or feature importance, like variable importance, does not mean causation. So even if you have a simplistic model, you can say, okay, this value, this variable, has a bigger effect on the outcome than the other ones. Sure, but it's not that it's a cause and effect thing.